Thank you very much for kind introduction, ladies and gentlemen. Good afternoon. So this talk is about gas nitriding of titanium scaffolds prepared by this additive manufacturing method, directly writing, and we want to improve mechanical properties, especially fatigue properties. So I'll be showing also some fatigue results. And this is the outline of my talk. First of all, I want to show you what these titanium scaffolds prepared by direct writing are. And then we tried high temperature nitriding of materials with low microporosity, and later on, this is the main part of the talk, we tried low temperature nitriding of materials with high microporosity. So titanium scaffolds prepared by direct writing, and scaffolds are metamaterials. You've probably seen them before. They are prepared by different methods. Here is the example from bone repair application. And the reason why it is used here is because when the defect of bone is larger than several millimeters, it cannot heal by itself. So you need something like this. And the method we use for producing them is not so well known. So these are some introduction. But actually, this is one of the additive manufacturing method where you can talk about printing, because this one has something called ink. And this is prepared by mixing powder, which can be same as for SLM or other methods, or you can use some irregular shape powder here also. And you mix it with polymeric binder and water to achieve very specific rheological properties, which allow you then use computer-aided design to print the object you want. And the final step then is to dry out the water, burn out the binder, and at the last step, you do sintering for consolidation. And as with other additive manufacturing methods which uses sintering, this allows you to control internal microporosity of material. So this is an example of two materials we prepared and tested in fatigue. And you see this one is sintered at 1400 for 10 hours, and we have very low porosity. We also have larger grains here. And this one, here we have microporosity of 15%. As you can see, we achieve open porosity across the whole printed filament here. We have one large pore and also some small pores which are isolated. And then we tested these materials under fatigue, and the surprising thing is that the porous sample with microporosity are much better. You can see here, for instance, at this level, the difference in fatigue life between them is 1 order of magnitude. And they differ in grain size, in microporosity, as you can see also in surface roughness. But the conclusion is that the reason why these materials are much better is this interaction of crack with pores, which leads to really highly tortuous crack paths, and this results in improvement in total fatigue life. Actually, crack initiation is faster in these materials, and I talked about that yesterday in more detail, so I'm not going to talk about it more here. The samples we tested were cylinders like this, and when you look at them, you cannot say if the microstructure of these filament is this or this. They look same, but the fatigue behavior is different. So what we can do is to try to optimize porosity. This is one thing we can try to even more improve fatigue life, and the other, which I'm going to talk about, is we try to improve crack initiation life by using nitridation. And the first trial we did was nitriding at high temperature of materials with low porosity. And as you can see here, these were nitrided at 1100 degrees Celsius for 2 hours, and we achieve nitriding layer of thickness of about, it's about 40 microns, I think. It's really very thick. And we try to measure hardness of these coatings at the surface, at the diffusion layer, and then in the core material, and we measured it also in different positions in these scaffolds. And these results here show that we are able to achieve homogeneous nitridation within this scaffold. So then we tested them under fatigue, and as you can see, with limited number of samples, these were not so good as sintered scaffolds, but given that this is really on the verge of low cycle fatigue region, this is actually good results. And the reason why they were not so good, and there are other studies, is that this nitriding layer is brittle, so after it fractures in, it introduces large initial crack, and the fatigue life is worse. So what we wanted to continue with was nitridation of these materials with open microporosity, because they were better in fatigue. And we want to create layer which is minimal in thickness, especially the compound layer of nitrides should be minimal. And it would be good if it provides higher strength, and also these are done to improve wear resistance. And this is our final goal. We want to potentially improve fatigue life of these materials. So the experimental program is quite complex, but we prepared single filaments or struts, as shown here, to be tested in 3-point bending, then disc for vertes and some other analyses, and full scaffolds for, here I have cyclic loading, as shown here, where we basically cycle between constant minimum value and then increase maximum level. This block has 50 cycles, just to get the response and see how the response of material changes, which here is described by the shift of the hysteresis curve, ratcheting strain, and change of the width of the hysteresis curve. So this describes the changes in stiffness of material and the energy consumed during cycling. So we observed that for these temperatures we tested, 500, 600, and 700 degrees Celsius, we achieved nitridation in all cases. These were for 10 hours nitrided. We don't see compound layer here. We see diffusion zone. It's the position in the filament is shown here. At 600, we do see some nitriding layer and diffusion zone, and here we clearly see double layer of titanium nitride and titanium 2 nitride. So, but it was also here, and what we obtained from XRD actually is that these 2 nitrides are present at all 3 samples. They are just not seen on, maybe it's very thin. Here is shown how the thickness of nitride layer changes. And here are the results from 3-point bending of single filaments. And this is kind of expected. You nitride them and the stiffness increases with increasing thickness of nitriding layer. But this is quite surprising because the strength is decreased. But this is maybe because it's open porosity, so we have really volumetric nitridation. So maybe, and here when it goes to strain, fracture strain, we see decrease compared to as sintered state, and abrupt decrease for 700 degrees Celsius. And when we observe fracture surfaces, the situation is similar to the samples, the compact samples I showed you. We observe brittle fracturing of this nitride layer, and we saw something similar even at 500 degrees. So it's, and here these are just preliminary results from block cycling because of differences in, there are some errors during printing, so we don't see really clear trend here or here, but when it comes to the absorption of energy, it's well discriminated. These samples in blue are as sintered. This is the only one which fractured, but you see they acquire or accumulate damage more quickly than nitrided samples. But we should continue with this. I tell you, these are just preliminary results on block cycling to see if it really can lead to improved fatigue life. So I'm sorry, it's many images and it's unfinished work, but let me summarize. We are able to do volumetric nitridation of these materials at temperatures as low as 500 degrees Celsius. Compound layer is composed of these two nitrides. We detected them for all samples. And we see that mechanical monotonic properties deteriorates, particularly at 700 degrees Celsius. And it seems that cyclic properties may be improved by gas nitriding, which we hope to see later. So this is everything. Thank you very much for watching.